Okay, Terry? You're muted.
All right, let me share my screen. There we are. How's that? Are we just seeing my title slide? Nothing else?
We're all seeing it.
Perfect. Hello. All right, how do we want to go this? Oh, let me start my timer so I know vaguely what my time frame is. So, hi, I'm Terry Stewart. I'm up in Canada, National Research Council, and I've been connected with University of Waterloo for a long time. My overall goal going into all my research at all is I'm trying to build large cognitive algorithms using neurons, in particular, also using things like basal ganglia, as Andrea was pointing out. And I'm really much focused on systems where there's lots of different brain areas trying to interact together, trying to do different tasks, mostly because, well, that is how brains work. There's lots of different parts interacting together. And the general approach that I take is this thing called the neural engineering framework. There's the tutorials for the Nango tutorials that are posted give much more detail on that. For now, I think the only thing to really focus on is I'm trying to do neural network models that do giant tasks, but I'm not doing something like make a big network and then do backprop across the whole thing. Instead, what I'm doing is taking an algorithm that would do the task, or coming up with an algorithm that would do the task, taking that algorithm, break it into components, build neural networks for each of those components. And when I build those networks, I might use backprop, I might use other techniques. But then you've got a whole bunch of different subcomponents you built, and then you combine them all together to make your one giant model, and that's what does the task itself. Okay. And so the thing that's a little bit interesting about this approach is I often have to like modify algorithms. So I can't like just take a normal algorithm that has a bunch of if statements and for loops and symbolic type operations. I can't take that and just and implement those components because neurons aren't particularly good at implementing those components. It's a pain to try to implement a for loop using neurons. And so there's a bunch of different ideas about what neurons are good at. One that I tend to use a lot is this thing called the neural engineering framework. And certainly what sorts of algorithms a group of neurons is good at is going to depend a lot on the exact neuron model, what synapses you have, what sort of connectivity you have. But across a pretty wide range of neuron models, it turns out that if I have an algorithm that consists of vectors, functions computed on those vectors, and differential equations computed on those vectors, it's pretty straightforward to take that and map it into, and map it into just whatever neuron model you happen to be wanting to use, spiking or non-spiking. We can make that mapping. It's a relatively automated process, and you get this nice thing where the smoother the function is, the fewer neurons you need to approximate it to a certain degree of accuracy. And by smoother, I mean how well it's approximated by low-degree polynomials. So that's sort of the background of where I've been coming from, and that's been relatively successful. We've built some fairly large systems out of that. The sort of the main one that we end up pointing to is this spawn model that came out in 2012. Which is large 2.5 million spiking neurons, 40 different brain areas, and it was able to do some basic tasks. That video you're seeing at the bottom left there is we visually presented it a sequence of numbers. It has to remember those numbers, and it has to report those numbers back out. In order to do that task, we need a vision system, a motor control system, some sort of working memory, some sort of control system that is tells it what to do at what time, how to control the flow of information throughout the network. So it's possible to build up something like that, which is fun and nifty and cool and all. And the part that I'm sort of that I get excited by is what changes did I have to make to algorithms in order to make that happen? And one of the things that ended up being really important in this sort of high-level task of representing a list of items is how do you represent a list of items? How do you do, here's a bunch of symbol, in normal computer science terms, this is easy. This is just an array, and you just append things to an array. That's easy. How do you do that when you're limited to sort of fixed dimensional vectors, and you don't know how long your list of items is? Ends up being a little bit tricky. And the particular approach that ended up working for us was this idea of what are called vector symbolic architectures. And the idea here is if I want to have a vector that represents some sort of symbol structure, so something like a red square, all right? So I've got some symbols and they're related to each other in some way. Then what I might do is I might have vectors for each of the basic terms in my language. So I might have a vector that means color, a vector that means red, a vector that means shape, and a vector that means square. And if I want to combine those into some sort of structured representation, I can just do some math operations on them. There's a bunch of different math operations you could choose, but you're going to do some math operations. You're going to get a new vector. And then from that vector, you can then extract out that original information. So if I have this vector and I want to know what the color was, then I can take that vector, I can do some more math with the representation of color, and I'm going to get out a vector that's kind of close to red. Okay. And there's a bunch of different systems out there that are like that. We chose this one in particular from Tony Plate, where the particular operations are vector addition and circular convolution. And the reason we chose that is because those functions turn out to be really, really easy to implement in neurons. They're exactly the sorts of things that it's nice and easy to get a neural network to approximate. All right, so that's background, gets us, that's sort of things that we've done before, and it's kind of cool. Oh, and I do want to also highlight that it's not just that you can use this to sort of implement the same sorts of things that high-level, old-fashioned AI type people have done symbol manipulation tasks for ages. It's not just that you can now implement those sorts of symbol manipulation tasks in neurons, but you also get some interesting new capabilities that are hard to do with normal symbol manipulation. So it turns out that with this sort of vector approach, it's really much more straightforward to do things like analogy and pattern matching, whereas those things are a little tricky to do if you're treating things as symbols.
Question from the audience, Terry. What is a circular convolution?
Oh, right. So it is just a weird math thing. It's one of these standard things that's built into all math libraries. So for some people, the right answer is saying, oh, it's a Fourier transform and then pairwise multiplication in the Fourier space and then an inverse Fourier transform. For some people, that's a helpful description. For others, it's totally not. For those that aren't, it's an operation where you're feeding in two vectors. I'm going to get out a vector. So let me compare it to addition. So in addition, I take two, say, 100-dimensional vectors, and I add those 100-dimensional vectors together. I'm going to get a new 100-dimensional vector, but that new 100-dimensional vector is still kind of similar to both of the original ones that I'm adding. So if I did the dot product between that output vector and my original vectors, it'd still be pretty high. So vector addition, we'd often think of as sort of, I'm taking two vectors and make me a new vector that's kind of similar to both of them. Whereas with circular convolution, I give it two vectors, I'm going to get a new vector out, but it's going to be wildly dissimilar to all of them in that it's going to have a very low dot product. I don't know if that's a helpful description at all.
But I think there's a question about the cost of that operation as well.
Yeah. So it is a linear operation followed by a bunch. So it's not. Sorry. Let me rephrase that. It does require pairwise multiplies. So it's a linear operation followed by a bunch of pairwise multiplies followed by another linear operation. So on some hardware, that's nice and fast to do. In Neurons, it's also relatively straightforward to implement.
And so Terry, it may also help to point out that circular convolution also preserves shift invariance.
Yes, although it's unclear how much of that we're actually using, but yes, that is also a very big yeah. And I guess the part that we really use in that is it preserves similarity in the input space. So if I do color convolved with red and color convolved with pink, if red and pink are originally similar vectors, then the resulting vector will also be similar. So it preserves similarity.
And Terry, just so that we connect this with the beautiful spawn work. So this is also used in the spawn network that you just showed earlier, right? This was the backbone of it.
Yep. So that is exactly how I'll say that a little bit more. That that's how we're going to represent this list, because instead of having color red shape square, it'll be something like position 1 is a 3, position 2 is a 7, position 4 is whatever, and that way you can extend the list as much as you want. It will, of course, become less and less accurate as you put more and more things in, but it'll be more of a gradual fading of accuracy. Cool. Thank you for those clarification questions. All right. So the point of what I'm trying to talk about right now is I want to talk about how do we represent space, how do we represent time. And so fine, we had this way of representing a list, and that's kind of an interesting starting point, and that's sort of research-wise where we started from. So what I would really like to do is fine, we had this list thing that represents sort of a one-dimensional thing going on forever, but it's really discrete. Like I'm representing, you know, I could have like something at position 1, position 2, position 3, fine. I could even represent something like something at position 1, something at position 2, something at position 27. No, that would also be, I could represent this way. But what I'd like, if I really want to represent space, I've got to come up with some sort of continuous version of this. When we were doing that in Spawn, we did have these vectors for position 1, position 2, position 3, but because we also wanted it to be able to extend indefinitely, we didn't just choose a random vector to mean position 1 and a random vector to mean position 2 and a random for position 3. Instead, we had some way of generating those vectors. And the way we did that was we said, okay, we generated an initial random vector that means position. And then we just combined that with itself to get position 2 and then position 3 and then position 4. So that way that there is some sort of semantic similarity between there's a relationship between position 1 and position 2 is the same as the relationship between position 2 and position 3. That was the intent there. And so this is basically what we had been doing, and I posted a question to my students in our online forum and said, hey, is there a continuous version of this? And of course, one of my students just immediately posted back, yes, of course there's a continuous version. That's obvious. Why are you even asking this question? Because of what I just sort of said earlier, that circular convolution is multiplication in the Fourier space. Right? That's you do the Fourier transform of your number, and then you do multiplication. And so if you want to do a continuous version of that, well, just do the Fourier transform, do an exponent in the Fourier space, and then do the inverse Fourier transform. And that would just be exactly the continuous version of what we'd already been doing already. Okay. So now what I can do is I can now make a vector that says there's an A in position 1.3, there's a B in position -0.2, and there's a C in position 1.7. Okay. There's slight abusive notation going on here in that I'm using this exponent to mean circular convolution exponent, but that's what we're doing here. So if you do that, and you do that math, and you get some vector S, and then you want to say, hey, well, what does that vector represent? Then you can do the same sort of thing of, we've been making these sorts of plots where we can say, all right, if I take that resulting vector and I ask, say, where is the C, I guess is what we're the example here. So I take that vector, I convolve it with the inverse of C, It's a pseudo inverse, but whatever. And then I try taking the dot product, how similar is that resulting vector to any particular position that I choose, right? So I can say, all right, is that result close to -5? No, it's not close to the vector for -5, but it is pretty close to the vector for 1.7, and it's also pretty close to the vector for 1.6 and 1.8. That's why it's got this nice smooth curve here. Importantly, there's no bounds on this representation, right? So I can extend this graph. There's no reason I did it between -5 and 5. I could extend it much larger. Here on the right is exactly the same math, just over a wider range. Yes, eventually, if you go out far enough, you can find peaks, but it's sort of like you'd have to go out sort of millions on the x-axis before you start finding other big peaks.
Terry, there's a clarification question on another. So what's the significance of convolving position with position?
It's just an arbitrary method for I need a unique vector for every position in my whole space, and this is sort of a smooth operation that will create a unique vector that means every single point in my space. There's probably other methods out there, but this one becomes, in the discrete version, if you only use the discrete points, it becomes exactly what we had been using before.
And is it also that, because you have these multiple positions multiplied, then you can do these inverse circular convolutions to go to the past, to pick points in the past?
Yeah, I don't want to say past yet. I want to right now say that these are different points in space, but yes, it does mean that when you've got a particular representation, you can either extract out the information from this point in space or other points in space. Okay, so it becomes a sort of a combined representation of all of that. All right. I was showing that in the one-dimensional case. There's no reason not to go up to the two-dimensional case, or three-dimensional, or four-dimensional. So if I want to start representing spatial situations of things, I can say, all right, I have a vector that means fox, I have a vector that means x, and a vector that means y. I say randomly generate those initial vectors. And then I can build up like a scene by saying, okay, there's a fox at this location, a dog at this location. The result of that is one single vector, and then I can ask that vector, okay, where is the fox, where is the dog, where is things? And these plots here that I'm now showing, those are the same as these plots, but just two-dimensional. So there's a vector for each individual point in the space, and I'm just showing the similarity between the result and each of those points in space. Okay. Cool, fine, that seems a little weird. What else can you do with this? Well, I've just shown over here that there is a vector that represents 2 points in space. Right, so it's a vector that's similar to 2 different points in space. I can also start defining vectors that mean regions of space. And so now I can ask questions like, what animal is in the middle of the scene? What animal's in the bottom right of the scene? And I get a resulting vector that is similar to all of the correct answers. So one thing that we did with that is just sort of explore what sort of spatial operations you can do on that. Interestingly, because it's just math, you can sort of do this comparison in 2 ways. You can either just do it by the math, or you can do it by taking the math and implementing in Neurons. As I commented, all of this math is easy to implement in Neurons, so the neural accuracy is pretty good to the non-neural accuracy. But then you can do spatial manipulations of moving objects around, asking what's in a particular location, and
Terry, actually another question. I'm actually also curious about this. How does the spatial proximity translate into the circular convolutions mechanism?
Spatial proximity. So certainly this blurring that you're seeing, so 2 points that are within sort of one of each other. So it's going to be hard for it to distinguish points that are within this sort of blurry area. There's going to be some resolution that it's going to have difficulty to go smaller than. But that's about the only thing that we've been finding.
And GERD is also action, and these figures look like those grid cell activations, and so can this?
We're going to get there.
To the health?
Punchline is going to be, yes, you can make this look exactly like grid cells. Yep. So we can implement that. So since this is sort of a weird representation of space, we also wanted to sort of say, hey, there's lots of other ways people have represented space in neural networks. Can we compare them? So here what we decided to do is just simply take a standard deep network, feed in we're going to be doing some sort of maze following type thing. We're going to be feeding in a current location, we're going to feed in a goal location, and we're going to feed in a signal that indicates which maze you're currently on, and then we're going to train up this network on like 100 different mazes, starting from all sorts of different locations and different goal locations. So just a big giant training task, supervised learning task. Learn this set of 100 different mazes, such that given a current location and a goal, the output of the network is what direction you should go. And then what we can do is we can vary the type of encoding that we're using. Do we use this weird encoding I just showed, or do you use sort of more standard ways of encoding space? And the punchline from all of that is this just outperforms all of them, and has the cool advantage that it's not limited to a particular window of space. So many of the other sorts of representations, you really have to pick, this is the window of space I'm able to represent. Okay. It just outperforms all of them, including if you just leave that encoding free and you let some neural network also just learn some sort of representation there. And then finally, as was sort of hinted there, if you take this approach and go ahead and implement it in neurons and go ahead and see what the neurons are doing, if you just do technically exactly what I just said there of randomly choose X and Y and randomly choose your neuron representations, you do not get grid cells. So if you just sort of naively throw this in and just sort of say, all right, just pick a random X and Y vector, the actual neurons that you get don't end up looking like grid cells. They look closer to place cells. But if you choose X and Y carefully, and if you choose this front layer of your inputs into your neural network carefully, it's relatively simple analytics, you get perfectly beautiful grid cells. And if you then take that system and you try to do the task of that everyone, that's been fairly clear that grid cells are good for in the past, which is grid cells are really good at generating place cells. If you try learning up the task, hey, am I at a particular location for a whole bunch of different locations? If you try training up that task, and if you choose your representation this way to make it look like grid cells in the brain, you get a huge improvement in accuracy on that am I at a particular location task. And it still preserves all of the other sorts of features, but you get better at this one particular task. I'm sure there's some sacrifice somewhere, but we haven't found it yet. Okay, so kind of a weird, interesting way of representing space. One of the plans, what I really want to do is want to be looking at how, if you start using this sort of representation and reinforcement learning type tasks, does that help and whatnot? That's sort of ongoing research that I'd love to do during August. I do want to briefly sort of also say something similar about time. And here we're going to do something slightly different. Yes, you could use what I was just talking about before, this sort of spatial representation, and have one of your axes be time. But that would end up sort of being a representation where I could also represent the future, and I could represent like really, really far back in time. And that's often not what we want. The particular task I'm looking for here is I want to represent a window in time. And this is the sort of thing that traditionally people have used reservoirs networks for. But I just want to sort of try, let's analytically go, I would really like to have a network that would be really good at computing functions of some window of time. But I'd already just said that the only thing that neurons are good at are this sort of functions, or at least not the only thing. Standard neurons, if I'm trying to use them, they're really good at functions and differential equations, but none of these things look like the sort of math that I wrote up here at the top. So how am I going to do that? Let's take the pure delay function. So let's take sort of the hardest version of this. What I would really like is a network whose output is whatever its input was theta seconds ago. All right, so that's sort of a pure version of that. And I'd sort of, okay, what can I do with that math? Well, if I take that math and I give it to a mathematician, they're like, I don't know what to do with that. Well, one thing I could do is I could convert it into the Laplace domain. Okay, just delays have a nice representation in the Laplace domain. I'm like, oh, okay, well, that really doesn't help me much. It's got this horrible exponent thing. What can I do with that? Well, there's a thing that you can do. So people might be familiar with Taylor series approximation, where you take any arbitrary function and you turn it into a polynomial and you sort of cut it off at a certain level. There's something a little bit fancier than that called a Pade approximate, where you can turn any function, you can approximate any function by a ratio of two polynomials. Okay, sure, I can approximate this function by a ratio of polynomials. Why would I want to do that? Well, the reason you want to do that is if you have a Laplace domain function as a ratio of polynomials, you can convert it back into a differential equation. So it gives you a linear differential equation where the state of this new variable m, which is a vector that is the number of elements in that vector is how many terms in the polynomial you've kept. You get this differential equation, and now that I have this differential equation, I can go and implement that using whatever neural network I feel like. In fact, it's a linear differential equation, so I don't even need a nonlinearity in my I could just have purely linear neurons and go ahead and implement this. So I can implement this in pretty much any hardware. If you go ahead and look at what it actually is doing, it's taking that past window in history of its input, and it's converting it into, or it's representing it using a Legendre basis space. So basically, one way to think of that is this variable m that has been created. The first element of this is actually just ends up representing, well, what's the average value over this window in time theta? And the second value ends up just being, well, what's the derivative, or so what's the average derivative in this period of time, or whatever. What's the slope of the average slope of the data over this window, and so on and so forth. And so you're taking however this input was, and you're representing it using these basis functions. So certainly, if the input varies very, very quickly, you will be bad at representing it. But if it varies, or you will need more terms in order to represent it. Okay. But it's a nice cheap network to go and implement. I can go and implement that with spiking neurons. Interestingly, and then to tie it back into the biology, if you go and implement this using leaky integrate and fire neurons, you end up with something that looks a heck of a lot like time cells in the brain. So there's been all sorts of tasks where you go ahead and give some stimulus, and then you go ahead and look at the neural activity, and you get this nice characteristic curve up here. So this top is from rodent data, where this is just showing the neural activity over time, where the initial stimulus happened at time 0, and we've ordered the neurons from where their peak is. And you get this sort of nice curve shape. This is what comes out of the model. Whoops. Interestingly, the precise shape of that curve is dependent on how many terms in the Taylor series in the Pade approximate that you keep. So this actually ends up saying something about exactly how close an approximation this is. This turns out to be 6, whatever. Okay, so that's weird. What can you do with that? First thing we did with that, because this is this is like, one way to think about what we just built here is sort of like an optimized reservoir. Like it's instead of having a reservoir, a recurrent neural network with random connections, instead you are finding the connections that do the best job of storing information over some window in time. We should be able to sort of apply it to sort of the same tasks that sort of recurrent neural networks have been traditionally applied to. And so we threw out a bunch of machine learning type tasks. First of all, if you throw it at exactly the task that this is good for, which is please output whatever the input was some number of time steps ago, then it just vastly outperforms everything. And so this graph on the left here is it's like 8 orders of magnitude better than LSTMs. It's just ridiculous. And it'll scale up to delay lengths of 100,000 steps. So the sort of things you just, it's very, very difficult to train a recurrent network to do. But that's sort of an artificial task that is just sort of exactly what we built the thing for. Over here is a sort of a more standard task, which is permuted sequential MNIST. So you take it's the digit recognition thing, but you're feeding the digits in 1 pixel at a time, and you're feeding those pixels in a fixed random order. So horrible task for recurrent neural networks to do, but the method that I'm showing here beats state of the art on that task. So that's kind of cool that this sort of is a very alternate approach of doing these sorts of time-dependent tasks. It also turns out to work pretty well for describing behavioral data. So if you get, this is behavioral data on, I present people with some sort of temporal interval, and I ask them to recreate the interval, or sort of to estimate how long the interval was. And you get these characteristic curves in the standard deviations of their estimates, and it's sort of flat for a while and then comes up, and that's exactly what we get out of the data, or out of the model. And we've also been comparing it to some neural recordings when people are adjusting the sort of average time intervals of these things. And we are also in the midst of mapping this. Certainly, these sorts of time cells have been found all throughout lots of different areas in the brain, but one place that people are particularly interested is the cerebellum. And we've been showing that if you go ahead and add in all sorts of extra constraints of making sure the biology is exactly right, or more right than we normally do in the Golgi granule microcircuit in the cerebellum, then we can also show it maps nicely onto that. Okay, that was a bit of a whirlwind of weird stuff. Take-home point that I wanted to say is, hey, here's an interesting, weird way of representing space, and we're finding that if we just use this as sort of a drop-in replacement for more standard ways of representing space, then we tend to find big improvements in terms of sort of machine learning type. Hey, how well is it good at this task? And it deals with the boundary problem really nicely. Same thing with this representing time. This is just sort of an interesting new tool that we can just drop in. And if you are wanting to do sort of recurrent neural network tasks that require outputs being functions of previous inputs, this seems like an interesting thing to try. Again, both of these things are very new, so I think a lot more work needs to be done, but I'm hoping to chat with all of you about that. And it's not particularly dependent on any particular neuron model, and you can even just use the math. So that's it. Thank you.
Thanks, Terry. That was wonderful. So there were a couple of questions, but I think you were actually starting to answer this with how this compares to reservoirs, and you answered that. And actually, I have a additional question. So when you train that network with the delayed MNIST task, for example, you're not actually back-propagating through these matrices, right? So
Yeah.
you're just using it as an input.
Yeah, you get to fix this whole, you fix the recurrent part of the network and just train this output. So basically you're getting this part is doing the recurrence to represent the past history of the input, and you just mathematically compute that, and then you only do training on these weights, the weights going into basically you need some nonlinearity there. So you do training on these weights, and it's a purely feed-forward training.
And how does this perform, and I'm asking some of the questions of the audience here, how does this perform on other tasks in MNIST, things like biosignals, audio, or even DVS data?
Yep. So we have been actually playing around with DVS data right now. One thing we have actually been seeing is so I don't think we have a strong evidence that this sort of thing is helping much over over something like an LSTM on DVS data, but we did find that using the spatial representation to represent the outputs was having huge improvements for like object tracking on DVS data and things like that. I think we haven't really found a good task to try doing this what temporal situations are needed for the DVS data. I'd love to.
Actually, Toby is asking a question.
Yeah, so,
oh yeah, go for it, Toby.
Yeah, so I'll just ask the devil's advocate question. Terry, this looks very lovely. It's a lot to sink in. Even for me, I've heard it. It takes a while to sink in. It's a bit too much. You have to cogitate it about a while. You're still trying to understand what the representation even means. But now this looks like the cat's meow, right? It's good. It's fantastic. You're just kicking butt on everybody. What is it not good for, and what does it cost you? If this is so great, why isn't everybody, you're just really like destroying all these benchmarks, right? Why isn't everybody just using this instead of LSTM?
Yep. So
there must be something bad about it.
Yep. I would love to know what that is. So it is definitely new. You do have to pick a time window. So you do have to know what sort of time window the system is going to be good at. I mean, you have to do a similar thing in reservoirs anyway. What else do we want to phrase about that?
But with these Legendre coefficients, don't you need a certain level of precision in order to?
Yep. Yeah. So you also need to know sort of the frequencies of inputs that you're going to expect.
I'm talking about numerical precision, right? If you're not going floating point, if you're really like dealing with fixed point.
Yeah. Then actually, one really nice thing about this. When you do this mapping into this linear space or this linear differential equation, you do get a free rotation that you can toss in there, and we've particularly chosen the rotation that is most numerically stable. So this thing ends up being really nicely numerically stable for even for pretty large matrices, but that does end up being an important aspect.
Terry, this is Andreas. I have a follow-up question on this, and I posted it on the Slack. Similar ideas have been proposed by Deneuve and Thalmaier, and you just really show an implementation here in terms of the neural engineering framework. Is that?
I think I would prefer to say that what we're showing, like this, turning it into this equation is a new thing, and that's not particularly neural engineering frameworky. Yes, you can take this equation, go ahead and use the neural engineering framework, but you could also take this equation and use it in lots of other different situations. So like when we've been doing the machine learning things, if all you want to do is compute a linear differential equation, you don't even need neurons, right? On a lot of hardware.
So the innovation here is basically turning from the time domain into a linear algebra problem. Yep. Through the Laplace transform.
Yeah, that's what I would argue. I mean, we only looked at, the neural engineering framework thing forces us to say, hey, turn everything into differential equations. But once it's in as a differential equation, I think it's useful in a lot of different domains. That said, I definitely really do want to highlight that this is new. We do not know where the limitations are. Oh, we do know one thing about these limitations. One of the things in the paper where Aaron developed this stuff first, he did try stacking this thing, which we call the LMU, Legendre Memory Unit, stacking LMUs and LSTM, LMU, LSTM, LMU, LSTM, stacking them that way, and that did outperform just a stack of LMUs. And it also outperformed a stack of LSTMs. So there is definitely something different that LSTMs are doing. And so there's got to be something that is better about them, but I don't think we have, or there's some situations that they're better in, but I don't think we have a good characterization of that yet.
Thanks, Terry. So we're also going to have a discussion session at the very end. So I think there are still a number of questions, and I have some on my own. But I think we have to move on with Benjamin's talk. But thanks, Terry. That was fantastic.
Sounds good. Thank you.
So